we have taken H, we have modeled it with some simplified H prime. This is my H prime down there. And then the two pathways the community has taken, which are rather distinct, is first to utilize what you have already learned in this class, which is the phase estimation algorithm. And I'll describe those steps in just a moment. This will give you the ground state and the energy of the ground state approximately. The second approach does something different and is known as a variational quantum eigensolver. And you will now find the literature replete with people talking about the VQE algorithm. And I want you to know what it is because there's a lot of talk about that. And this will give you a state psi, which might be, if you're lucky, close to the ground state, and an energy which might be, if you're lucky, the ground state, but has a certain guarantee that this energy will be no smaller than the ground state energy that you're looking for. Okay, so let's look at these two different routes one at a time. The first approach, phase estimation, is very simple to understand, as I described, because it is no more than the application of phase estimation. We start with a register of qubits where you're going to store the eigenenergy. So this is determined by the precision that you want, the number of qubits. You start out also with a state, psi, which is some approximation of the ground state, but you don't know how good. So it's the ground state plus epsilon times some other component, which is orthogonal to the ground state. And allow me that you have prepared this somehow. And you may prepare it badly. That's still OK. What you do is you perform, remember this is going to be some sum over all values k. You perform a controlled h to the k operation over here. This is feasible because I've shown you how to trotterize. But this is really, really painful because you now have to trotterize and also trotterize to the kth power. So now you have to rerun that trotterization an exponentially large number of, or span of energies, for example. Okay? But allow me this. And we know from the phase estimation algorithm that what you get as an output over this is going to be a sum over energy eigenstates and then phases which are on the order of some constant over E sub k. So these are going to give you the energies of the system. This is the top register and this is the bottom register. And there are some coefficients. And when you measure this top register after the quantum Fourier transform, you collapse into an eigenstate down here. And if your initial overlap is sufficiently large, so epsilon is small, then you get the ground state that you desired. And you will have a measure which is the energy eigenstate. But by the way, this is exactly Shor's algorithm. This is the quantum factoring algorithm, also being used for quantum simulation. It's actually not accidental that all known exponentially fast algorithms today, quantum algorithms, are essentially the structure of Shor's factoring algorithm. You put something in superposition, you do controlled something to a high power based on the superposition, you do the inverse quantum Fourier transform. So if you know Shor's factoring algorithm, you essentially know this whole route to quantum simulation. Why is this challenging? Well, first, it's good because you get the eigenstate and the eigenenergy, the ground state, right away. But the challenge is that you need a perfect quantum computer with long coherence times. There's a beautiful analysis of the requirements by Matthias Treuer and company from ETH, now at Microsoft, where he shows that if one uses this phase estimation approach, one has a chance of simulating nitrogenase, exactly what I started today's lecture on, if you can run the quantum computer for about a day, okay, with a relatively fast clock cycle as well. The longest coherence time we have for many of our quantum bits, like in superconductors, is on the order of a millisecond. And for ions, it's perhaps tens of seconds. So a day is a bit of a stretch right now. And this might need something on the order of 1 million qubits as well. Whereas in our actual deliverable quantum computers, companies are talking about maybe 50 qubits today. So that gives you an idea of the gap between the ideal system needed and which is actually available.